Today's lesson focuses on significant figures. This is a very important lesson that will give you a good baseline understanding of how to do calculations and round your answers to the final number of significant figures. When we do any kind of calculation in science, we are always taking measurements in the lab. And as we take those measurements, there is an amount of uncertainty associated with our measurement. This happens in chemistry, this also happens in physics, and this also happens in biology, although lesser so because we don't do as many calculations in biology. So for example, if you were taking a measurement of a volume in a graduated cylinder and you had a bunch of graduations here and you were measuring the bottom of the meniscus, this measurement right here, you would be estimating to 1 or 2 decimal places depending on the tool that you're using. And as you estimate and record your value to however many measurements, you are actually measuring them to a certain number of what is called significant figures. So we want something that, or we want a measuring tool that is accurate and precise. Okay, and we'll talk about those definitions in a bit. But for example, if we have a scale that measures to 3 decimal places, this is good. A ruler that measures millimeters as opposed to just centimeters, so that has more graduations on the tool, this is better for us when we record numerical data. When scientists report measurements, they report all the digits that are accurately known, plus 1 digit that is uncertain, or in our minds, that is estimated. And all of these digits collectively are called significant figures. The more significant figures you have in a measurement, and all that means is that you'd have more decimal places, then the more precise it is. So for example, if you could pull out a ruler and measure the thickness of a piece of wire, 2.46 times 10 to the negative 2 is far better and far more precise than just saying 2 times 10 to the negative 2. So we're always trying to collect as many decimal places as possible when we record numerical data. The terms accuracy and precision are used a lot in science, and lots of times students use them incorrectly. So what is the difference, right? Accuracy is the measure of how closely a result approaches the accepted value. So I think of boiling water, for example. And if I put a digital thermometer in, we know that if water is boiling, okay, so here it is, and there's, gas bubbles here because we're heating it up and it's boiling, okay, steam's rising. If I put a thermometer inside that beaker and I measure the temperature when it's boiling, we know that that temperature should read 100 degrees C. But sometimes with digital thermometers, anything that's digital, they get knocked around, bounced around. They don't read exactly as they should. So if that thermometer was not reading exactly 100, we know that it's not exactly accurate. Okay, so again, how closely a result approaches the accepted value. Precision refers to the uncertainty in a measurement. So this could be the number of decimal places that you record, but it also could mean the exactness of a measurement. So if you were trying to get a boiling point of water and you were using many different thermometers, if they were all recording exactly 100 degrees C, you know that they're also precise. Okay, so we keep reproducing the same value. That is good. If they were all reading 95, which is not accurate, but they were all reading the same value, they're still precise because they are reproducing or giving us the same exactness of a measurement every time. So recognize that with precision, sometimes values can be precise but not accurate, and sometimes they can be both precise and both accurate. Here's a good example to explain the difference between accuracy and precision. If you're playing darts and you're trying to hit the bullseye right here, and you throw your darts and you see here that based on this image, you've hit the bullseye, okay? They are accurate because that is what you are going after, okay? If you're trying to get exactly your dart exactly at the bullseye, they've done that. And then with their 3 darts, they've been able to reproduce that data. So each time that they threw that dart, they got the exact same measurement. So that means that they also have good precision. Here is an example where let's pretend we're still aiming for the bullseye, okay, over here. They're nowhere near the bullseye, so they are not accurate, but they were able to place their darts in the same spot. So they, again, exactness of a measurement is happening, or reproducibility. They're able to reproduce the same measurement, even though it's not the one they want. So here's an example where we have bad accuracy, but we have really good precision. And then in this last example, again, if we're going for the bullseye, okay, you can see the darts are nowhere near, so it is not accurate, but the darts are also nowhere near each other. So we are not reproducing that data or that, whatever value we want. And the exactness of the measurement is not anywhere good. So here's an example where we have both bad accuracy and bad precision. Moving back to the values that we actually record. So once we record a piece of data or a numerical value, we hope that it is both accurate and both precise. And then from there, we actually need to know and label the number of significant figures in our value. And this is very important because you will be doing mathematical calculations with these values. And the way that you round your final answers is based on these rules for determining significant figures. So the first rule, any non-zero digit is counted as a significant value. So again, accurately measured plus the last one is estimated. So here, 392, all those digits count. They have 3 significant figures. 1,589, there's no zeros in there. All of them are counted as significant. So again, I don't know what they're measuring, but 158 is accurately known, and we assume that that 9 has been estimated. Zeros between non-zero digits are significant. So here's an example. So 3,005, we count all of those. We say that they have 4 significant figures. 50,201, everything counts, 5 sig figs. 20.61, everything counts, 4 significant figures. Now, it's the zeros, and depending where the zeros are placed in your value, that may or may not be significant. So a leading zero, okay, so 0 to the left of the first non-zero digit in a decimal. So take a look at these examples. You notice they're all 0 decimal something. These zeros are not significant. So right here, these are our leading zeros right here. There's 3 of them. They are not significant. They're not actually measuring anything. They're just holding a place, and they're implying that we have a very small value of whatever, mass, centimeters, whatever it is that we are actually measuring. So right here, the very last 2, 3, 8, are the only ones that are significant. And so that value has 2 sig figs. Here again, I have 1 leading zero, doesn't count. It's just telling me that I have a small number. So 587 are the values that were accurately measured, and the last one estimated, 3 sig figs. Here again, I have 2 leading zeros. They don't count. Everything else would be significant. That's 4 significant figures. Here's all kinds of leading zeros, and then the last digits are significant. So we have 3 sig figs in that answer. If you have zeros at the end of a number and you have a decimal place in that value as well, then those zeros are going to count and be significant. So this is important. There's got to be a decimal with a 0 at the end of the number. So here's an example here, 35.70. This digit right here has been estimated and is part of the measured value. So we have 4 significant figures. Formatting issue here. Here's my value right here. So I have some leading zeros. Leading zeros don't count, but anything afterwards, even if there's a 0 at the end, has been accurately measured and estimated, this last digit. So we have 3 sig figs. Next value, 2.660. There's a 0 at the end, but it's after a decimal place. We would count that. That has 4 significant figures. In this value right here, I have a leading 0. Leading zeros don't count. Everything else is accurately measured. The 0 at the end is after a decimal place, so it counts. I have 4 significant figures. So when do zeros not count at the end of a value? Well, it's when there is no decimal place, okay? And they may or may not count, or they may or may not be significant. And sometimes we add a decimal to indicate their significance. So here is a good example. So the number 5,600, and notice there's no decimal there. So what this tells me is, I don't know if they've measured, let's say people in a crowd, okay? So a big crowd. And do they know that it's exactly 5,600 people in attendance? Or is it like, 5,550 and they've rounded up to 5,600? Or are they just guessing and they think, oh, we think it's 5,600? We need to have accurate values. So when we see something like this, 5,600 with no decimal place, we can only go based on these 2 values right here. And so at best, really, we say that we have a value with 2 significant figures. And then depending on how it's been measured, again, maybe we can say it has 3, maybe it can be 4 if those zeros are significant. In science, we do not like numbers like this, okay? We do not like values with no decimal place because it is vague. We're not sure how they got the value. So we try to put a decimal place in as often as possible. Here's another example. So just 20. So again, we don't know, is this exactly 20 degrees? Was it 19.5 and they rounded it? We don't know why they would round. 19.5 is far better than a value of 20 with no decimal. So we say it either has 1 sig fig or maybe 2, but again, we can't really rely on that. We'd have to go with the lower value of 1. But then you're going to notice down here, we see 20 with a decimal. So when I see that, then I know I have exactly 20 of something, whether it's 20 people or, maybe a temperature measurement of 20. I don't know why it's not to 1 decimal place, but that could be because the tool that you're using is not as precise. And here again, I have the value of 100. And when I see a decimal after it, we can say with certainty that all 3 of those numbers are significant. And again, just to recap, the more significant figures, the better. Because when you do calculations and you have to round your answer, you can round then to more significant figures, which will give you a better value. I now want you to stop the video and go into the booklet on significant figures and practice any worksheet that has you determining the number of significant figures. This is crucially important that you have a good understanding of that before you move on to calculations. Now that you know how to recognize the number of significant figures in a value, we're going to show you how to do mathematical operations and round your answers properly. When we carry out mathematical operations with data in a chemistry lab or a physics lab, we are to round our answers to significant figures. And when we do multiplication and division, we round our answers to the fewest number of significant figures or digits. Sometimes they use the word digits. This is why you need to be able to recognize how many significant figures are in your values. And if you don't know how to do that, don't keep going here. Stop the video, go back and practice a little bit more. Otherwise, you're not going to be able to round anything properly. And I just want to point out that rounding to 2 decimal places is not a good way to round answers. You have to round to significant figures. So let's look at this first example. I have a value of 2.8, which has 2 sig figs. And then I have a value of 4.5039, which has 5 sig figs, which is great. But I cannot give an answer that is more precise, because remember, the more decimal places is precision, than the least precise value that I have. Your calculator does not understand significant figures. You punch this into your calculator and the display shows you all kinds of lovely decimal places. But now that you know the rules of significant figures, you have to round to 2 sig figs, which will force us to round to 13 as a final answer. Here's another example where I take a division. So this value right here has 3 sig figs. This value right here has 5. That's great. But again, I cannot report an answer that is more precise than my least precise value, which is this one right here at 3 sig figs. The calculator has no idea. It gives me all kinds of decimal places, but you now are aware of these rules and the limits of precision. You're going to round to 3 sig figs. Now you have some leading zeros. They don't count. So you would round to 0.0611. For the next three calculations, we'll do them together. We take 0.86, which is 2 sig figs, and we're going to multiply by a value that is 4 sig figs. So you multiply them in your calculator, and again, the calculator is going to give you all kinds of values. You have to round to 2 sig figs. You are rounding to the value of 27. The next one uses scientific notation. Doesn't matter. You still plug it in as you've been taught. The first value has 3 sig figs. The second value has 4. That 0 counts because it's after a decimal. So you multiply those together and you get an answer that is large. In your calculator, you need to round to 3 sig figs. So I'm just going to write the whole thing out. And I have no choice here. I have to go into scientific notation because I need 3 sig figs. So I'm going to say 1.16 times 10 to the 3. The last value or the last calculation that we have there, 5.6670, we're going to multiply by 0.0578. You have to know the rules for significant figures. Right here, this is my lower one. I only have 3 right there. I have to round my answer to 3 sig figs. I have a leading 0, which doesn't count, and I'm going to round to 328. Don't forget that if you have a 5 after your value, 5 or greater, you round up. Below 5, you round down. When we are asked to add or subtract values, this is different. Okay, so multiplication and division deals with the fewest number of significant figures. Now we deal with the fewest number of decimal places. So here's an example where we take 3 values, and I don't care how many sig figs I have, I care about decimal places. I have 3 decimal places there, I have 1 decimal place there, I have 2 decimal places there. The calculator does not know about rules of significant figures. You have to round to the fewest number of decimal places. So you're going to chop your answer there. There's a 5 after the 1. It's going to cause us to round up. We end up with a final answer of 132.2. Doesn't matter how many values you have before the decimal. Doesn't matter how many significant figures. It matters for the number of decimal places. So the next example, I have 2 decimal places there and I have 3, which means I need an answer to 2 decimal places. So we're going to add these up. And the calculator gives me 3 decimal places, but I know I'm not paying attention to that. I'm paying attention to the rules, and I'm going to round to 11.68. Here again, I have some scientific notation. Make sure you're punching it in properly into your calculator. And even though you have scientific notation, you have 1 decimal place there. You're going to report your answer. So 3502.9 has to be rounded to 1 decimal place. Here we're going to subtract. I've got 2 decimal places there, and I have 3 in the second value. So I need to report my answer to 2 decimal places. So we punch it into the calculator. We're getting an answer of 39.689. So we're going to round to a 9 as my final answer.